All right, so hopefully you saw the latest assignments are graded. I was a little bit friendlier. Still gave nitpicky feedback, but so hopefully all of you are improving your writing because you're going to start doing less and less writing in here because now we're going to start coding, which is maybe a good thing, maybe a bad thing. So we'll see what happens. So let's pick up where we left off last time and then hopefully get into the programming stuff real quick today. All right, so if you remember last class, we were talking about the Y2K bug. We were talking about the cost of memory. We freaked everyone out with how much memory cost in the 90s and how it had already come down in price. So, you just use your imagination of how expensive memory was before that. I think I mentioned the Bill Gates quote of "You'll never need more than 32 kilobytes of memory." So back then, 32 kilobytes was probably thousands of dollars worth of memory. It's almost like when you buy a boat. When you buy a boat today, you buy the engine and it comes with a boat. It's like pretty much what you're paying for. So back then, you were buying memory and it came with the rest of the computer. Is the real thing. Today, whole different story. Memory is very inexpensive today. And we have more of it than we typically need for a majority of our tasks. Now, with that in mind, though, we have to remember that, well, we have to consider that the modern programming languages all came from the C programming language, which means that they all have built into them defenses against, well, the ability to be able to be good stewards of memory, right? So they have the ability to store numbers in different ways. So, and this is really the intro into variables. So here pretty quickly, we're going to be getting into how do we represent memory, asking questions, repetition in these programming languages. I'm going to try to show you as many of those things as an initial, hey, here's what it is today, and then we'll fill that with the details. But effectively, if you have a programming language and you want to remember numbers, you want to remember whole numbers like the number 5, the number 7, things without decimal points, okay? We have multiple ways of doing it. We're going to talk about why here in a second. So a byte is a signed 8-bit integer. A short is a signed 16-bit integer. An int is a signed 32-bit integer. A long is a signed 64-bit integer. And I'm even going to throw another one in here right now called a char. A char is an unsigned, I'm going to say 8/16-bit integer. We'll talk about that here in a minute. Because one of the things we're going to be looking at in the first 20 minutes of today's class is languages, some comparisons between languages that you're going to be learning and getting jobs around. And if you remember from like day one of class, I mentioned something along the lines of programming is the skill set, the language does not matter. I'm hopefully going to be able to show you that in a slide I created here that shows hello world, simple programs in like 4 or 5 different languages. And you're going to see they basically all look like the same thing. All right. So in any case, if we take a language like C and like C++ or like Java or like C#, so really all of our modern compiled programming languages follow what we're about to talk about with these guys right here. They all have a bunch of different ways of holding whole numbers, signed whole numbers. What signed means is it can hold both positive and negative numbers. You can represent the number -13 as well as the number +13. That's what it means to be signed. An unsigned number is it can't hold negatives. It holds, you know, a 17, a 34, but it can't hold a -2 in an unsigned value. And it'll make sense why we choose that. Ultimately, the punchline still comes down to memory. If we want to be able to hold positive and negative numbers, we're going to use one of our bits of memory to represent the positive or negative, which means that we can hold one level of magnitude smaller values. All right, so like an 8-bit signed integer can hold values between -128 and +127. Where if we had an unsigned version of that, it can hold 0 to 255. It's the same number of unique values. It's just one of them lets us count higher because we're only on the positive side. The other one lets us not count quite as big because we have to accommodate the numbers on the negative side. All right, and if you were paying attention to the numbers I mentioned with like a signed 8-bit integer with bytes, this guy can hold -128 to +127. That's the range of values that can fit inside of a byte. So again, for time, but also because you're going to talk about this in the 325 class next semester, the reason why there's one bigger value on the negative side than there is on the positive side is because the way we represent positive and negative number, really the way we represent negative numbers in modern computing is using something called the 2's complement, which you'll learn about. It's not really a topic for this class. In fact, a lot of these things are not things you're going to have to like memorize. Again, it's foundational information. And again, when we go to do the exams, I'll tell you what things you should focus on and what things are not going to be things I test you on. So as an example, I'm not going to ask you on an exam, what's the range of values a byte can hold? Realistically, once you have the foundation, you should be able to figure it out, right? You know, it's 2 to the 7th power is the 128. That's where that value came from. Okay, well, the reason why when we use 2's complement to represent signed numbers, we get an extra value on the negative side has to do with us not wanting to represent 0 twice. We don't need to have a positive and a -0. 0 is 0. So in the old days of representing negative numbers, we would have just used one of those bits to be a positive or negative sign. So on the far left, if it was a 1, it would be a negative number. If it was a 0, it would be a positive number. Okay, but that ultimately means that you have both a positive 0 and a -0, which seems to be like inefficient, right? We don't need 2 different ways of talking about nothing, talking about zeros. So this 2's complement thing, which has you flipping all the bits and adding 1 to it and doing all this stuff with what's called bitwise operations, which is something you'll talk about inside in the computer organization class, seems much more convoluted for a human being to do, but it's fast for computers to do it. And then we don't have 2 different representations of 0. We have a single representation of 0, which then gives us 1 extra number on the negative side. Free up that space to get us that -128, which in your career you won't have to think about realistically. Again, it's under the hood foundational stuff because today we have lots and lots of memory. Shorts, this is negative. Negative 32,768 to positive 32,767. Now, I will test you on this one. The larger the numbers get, the more you have to memorize them. I won't test you on that. All right. What you'll find is this first number is roughly plus or minus 2 to the 7th power. This number is plus or minus 2 to the 15th power. This number will be plus or minus 2 to the 31st power. So this is roughly minus 2.1 billion to positive 2.1 billion. So if you look at 2 to the 31st power, That's just multiplying 2 to the 31st power. There's our 2,147,483,648. So it stores that on the negative side all the way up to 2,147,483,647 on the positive side. Okay. Along negative giant number to positive giant number, I think it's like 16 quadrillion. So if we do 2 to the 63rd power, it's 9. So it's -9. So let's see, that's thousands, millions, billions, trillions, quadrillion, quintillion. So it's 9 quintillion, 223 quadrillion, 372 million, billion, 36 million, 800 millions, billions, trillions, quadrillion, quintillion, 9 quintillion, 223 quadrillion, 372 trillion, 36 billion, 854 million, 775,808 on the negative side to positive 9 quintillion, 223 quadrillion, 372 trillion, 36 billion, 854 million, 775,807. That's the range of values. So we'll say negative giant number to positive giant number. All right. But again, you're seeing the pattern: 2 to the 7th, 2 to the 15th, 2 to the 31st, 2 to the 63rd, based on the number of bits we're using to represent the value, where a bit is a 0 and 1. So if I have 64 zeros and ones to represent numbers, that means I can hold 2 to the 64th power unique values. Remember, we looked at the conversion stuff. We saw that, octal, we can store the numbers 0 through 7 as 3-bit values, and each permutation of 3 bits lets us uniquely represent a single value, which we've decided is one of the octets, one of the values in the octal numbering system. Where we go to hexadecimal, we use 4 bits. So every single permutation of 4 bits lets us represent exactly 16 unique states, which we happen to apply to the hextet, the hexadecimal numbering system, 0 to 9, A through F. Okay, so our numbering systems are effectively ways for us to represent value, whether it's magnitude if we're doing math, or just unique states. For instance, binary, 0s and 1s, we use that not for doing math, not just necessarily in computers. We use it for on, off, the state of a transistor. All right. Sometimes we might use binary for doing math. We might add two binary numbers together. But when we're dealing with, the binary value for a circuit, a transistor, it's 0 is off, 1 is on. Is electricity flowing or not flowing? A light switch. On, off. Make sense? All right. So punchline here again, I won't ask you to memorize these specific numbers. What I want you to appreciate is in our modern languages, they have been built on top of much older languages, which have facilities for storing values in a, I think I referenced at the end of class last time, kind of like Tupperware. You grab when you have leftovers, you grab the piece of Tupperware from the kitchen cabinet that's kind of the right size for the food you're saving, right? And we just do that because we have limited space in our refrigerator, right? Just like computers used to have limited amounts of memory. So we have this is, in this case here, 4 different sizes of Tupperware. And we want to pick. Historically, we would have picked the right size to hold the data we were storing. So if I only needed to store a value in this range right here, well, I'd be wasting space. If I was going to, save a little bit of leftover broccoli, I wouldn't pick the largest Tupperware container in the cabinet and throw 3 pieces of broccoli in it, right? Yeah, you would just throw it out because broccoli is not a food. I actually like broccoli. It's greens up your steak. So in any case, historically our languages had these built-in facilities to allow us to pick the right Tupperware. Okay. But now, since memory is cheap and we have lots of it, modern programmers typically don't think about this. But what I'm telling you is the difference that a computer scientist who has a degree and has the theoretical understanding, they know how to consider this if they need to, which there will be problems you will run into where size of the data you're storing does have a significance. But a majority of the time when you're programming, if you're holding a signed whole number, just some integer, you'll put it inside of an int. If it's the number 7, you'll still put it into an int. The 3 pieces of broccoli inside of the giant Tupperware container, who cares? I have 4 zillion Tupperware containers. And my refrigerator is of infinite size for all intents and purposes. That's the world of a computer today. Okay? So typically, if you're holding a whole number, positive or negative, we store it in an int. If that's not quite big enough, if 2.1 billion doesn't accommodate what you're wanting to store, you can store it inside of a long, which they do get used. Longs get used. Shorts never get used anymore. So a long can hold up to, what do we say, 9 quintillion, big number. Okay, realistically, if you're starting to play in that space, you're probably writing some sort of scientific simulation or something like that. Things that immediately start becoming very, very mathy. And realistically, at that point, if you're programming in that realm, you would have to wrap your mind around this stuff because it starts becoming important. Your 32 gigs of RAM in your computer is no longer effectively infinite RAM when you are trying to represent some, gigantic mathematical simulation problem or something. Okay, but if you're writing a video game or some business application, chances are you're not getting up into the quintillions, right? Like the number of rows in a spreadsheet. My guess is that Microsoft Excel probably only supports 2.1 billion rows on a spreadsheet. Maybe they've made that decision. If they're extra nice and want to future-proof it, maybe they decided, oh, we'll go ahead and let them have 9 quintillion rows, which I'm guessing you couldn't fill in a lifetime or multiple lifetimes. So we're going to say that's good enough for a while. All right. So modern normal software, 99% of the software you're ever going to see is facilitated by these couple of storage types. All right. A short never gets used anymore. Again, this is something from yesteryear when we're like, okay, well, I need to hold a value bigger than 127, but smaller than 2.1 billion. So that my next size Tupperware, we always have that weird size Tupperware in your cabinet that you hardly ever use, but it seems like the sets always come with the most of those. Why is that? My cabinet, I have like 40 lids that are these little square containers like this, but they're super shallow. Like, what's that for? But I make way more sauce than that, and when I make it, I eat it because that's also doubles as a beverage. Well, I mean, sauce and like coffee, they're both hot liquid. It's fine. Like, man, no wonder Lippman has a weight problem. Guy drinks gravy. All right. So in any case, that's our comparison. So in your career, you will likely never create a variable of type short. If you ever work with a variable of type short, it's because you're manipulating or using some older software and you're making changes to it, something like that. All right. So we have 4 different ways of storing the identical type of value. Right? It just stores it in different size pieces of Tupperware that we used to care about back in let's say the 50s and 60s. All right. And all of our modern languages have just inherited these what are called primitive types, and we'll talk about that. All right. So that means in Java, you can create a short. In C++, you can create a short. In C# you can create a short. Nobody does, but you could. Why? Because they're built on, they're effectively enhancements of the old C programming language that have just added some other quality of life features to make programming a little bit more convenient. All right. And we'll talk about that as we get through it. All right. Now we get down to a char. A char holds an unsigned integer, meaning we don't have to hold positive and negative values. Okay. So when I say char, what I'm really talking about is storing a character, right? Now, computers are really, really, really good at working with numbers. But human beings, while we can tolerate numbers, you can already think about it like when you're making a phone call, okay? I tell my phone to call mom, okay? I can make a reasonable guess, probably get more than half of the digits right of my mom's phone number, okay? But in general, we don't memorize numbers anymore. We know names, right? We like letters and stuff better than numbers. So that's something that sometimes as a person, those are the kinds of values we want to store, is characters. Well, computers like fine, will let you store characters, but at the end of the day, we're going to hold a number. All right. So computers, they have these various memory buckets, various types of memory, and they all hold bits. So any way you cut it, it's holding a number. Now, what we've done for the character type is there is a lookup table where a number gets mapped to a character. Old days, 8 bits was something called the ASCII character set. And if you were to go and look this up, here's the ASCII character table. So the 8-bit value, a bunch of zeros, is the null character. Here, let's just get to the alphabet. So here's a capital A. A capital A is the decimal number 65 or the binary number 0100000001. All 3 of these values here are all the same number. This is decimal. This is, what is that, octal next? Octal, then hexadecimal, then binary. So 65 decimal is equal to 101 octal, which is equal to 41 hexadecimal, which is equal to this series of zeros and ones in binary. Those are all the same value, just different ways of representing that value. Make sense? At the end of the day, when we're talking about computers, they store the values in bits. All right. So a human being might say, oh, the 65th ASCII value represents the letter A, capital A. But in a computer, that's all these binary values. Okay. So this is a lookup table called the ASCII table, American Standard Code for Information Interchange. Because way back when, the people who created this stuff said, you know what, the only language in the world that means anything is English. So hence ASCII. And actually in the early days, there was only 128 things in there. Then they added some stuff for like playing cards and smiley faces and stuff like that, to fill it out, because, why add more language stuff when you can just make up stuff, right? Because those other languages not important, right? Modernly, though, we have something called the Unicode character set. And Unicode has 65,536 unique characters. That's 0 to 65,535. So we can represent 65,536 unique symbols. The first 256 of them are the ASCII character set. After that, we start having the symbols and stuff from other languages. All right. So Unicode would be considered what's called a superset of ASCII. Relatively unimportant from I'm going to sit down and program thing, but knowing that this is what's happening under the hood lets you do some cool stuff. For instance, you can write a numerical loop that goes through the alphabet. You don't have to know what the numbers are under the hood, but knowing that they are numbers under the hood, you can say, I'm going to start at an uppercase A, and if I add 1 to an uppercase A, I get an uppercase B. 65 plus 1 is 66, which is an uppercase B. Make sense? If I subtract 1 from that, I get the the at symbol. Okay? Starting to make sense how this mapping works? Computers ultimately are storing it as a number. But since we wanted to, at runtime, get mapped to something that's familiar to us, because if we just saw a wall of zeros and ones and they say, oh, well, that actually is an uppercase A, we probably believe them, but then we change majors. That's not comfortable for humans, right? But if somebody shows us an uppercase A, oh, we're cool with that. We don't really care how it got to that A for us, all right? And the way it's doing is it's storing a number, and when we ask for the value of that variable, since the value, the type of variable we're dealing with is something called a char, it's going to go ahead and, as an intermediate step, go and look it up on the appropriate table and give us the actual character represented by the number it was remembering. That makes sense? Older languages use ASCII. The more modern languages use Unicode. All right. So in older languages, we had, this was 0 to 255. In newer languages, this is 0 to 65,535. Which I think you'll find is these two numbers, the absolute value of those two numbers added together, will get you 65,535, because we're using all of the bits for the magnitude of the value. We're not storing a sign. Why? Because if I have this ASCII or this Unicode chart, not that they couldn't have stored things as negative numbers, but sort of kind of doesn't make sense if you're a human being and you've created this chart like a lookup table, and somebody says, oh, give me the character at position -17. Like, why did you let it go into negative? The negative aspect of that is more of a mathy thing, right? So really, you're going to say, look, I'm going to represent 65,536 unique characters, and they're going to be numbered 0 to 65,535. Where 0 is this character, 1 is this character, 2 is this character, 65,535 is this character. Make sense? So we don't need the negative numbers. We just use the entire bit space, all 16 bits, to store positive numbers. Or really, it's unsigned numbers. They're neither positive or negative. We just ignore the fact that that's something that even exists. We have 65,536 unique values that we can represent with 16 bits. Okay, that's the number of unique ways you can draw 16 zeros and ones, 65,536 unique ways without any duplicates. All right, so the char primitive type ultimately for us means a character, but it's being stored as a number behind the scenes. Then we have something called a float and a double. You can think of floats as the decimal point int, decimal point long. All right, so this is kind of a very similar argument to what we just talked about, except we can all agree that sometimes when we're dealing with mathy stuff, we need to hold values with decimal places, like 3.14, right, for pi. All right, a whole number isn't going to cut it. All right, so we need types in our languages that can hold decimal point values. So a float is 32 bits signed before decimal point, 16 bits unsigned after decimal point. So before the decimal point, the first part of the number, we can hold the same size values that can store in an int, plus or minus 2 billion, 2.1 billion. After the decimal point, when we talk about the precision of our value, we're representing that as the same size. Well, we're representing that as the same thing as a char, because we don't have negative values after the decimal point in a decimal point value, right? The negative is always on the far left before the decimal point. So after the decimal point, we use all 16 bits of that for representing the value after that. So that's going to be 0 to 65,535. Make sense? Which means the entire bit space used up by a float is 48 bits. 32 bits before the decimal point, 16 bits after the decimal point. Effectively, if you're mapping this in your mind, this is the floating point version of an int. It doesn't hold as big of a value as double does. Make sense? Okay. Again, understand these different sizes. I'm never going to test you on these different sizes, but you should probably have an understanding that a short can hold bigger values than a byte. An int can hold bigger values than a short. A long can hold bigger values than an int. A char only holds positive values because it's part of a lookup table. Floats can hold decimal point values, but they're sort of kind of like integers in that they can hold values up to a certain point, but sometimes we're going to need bigger values. And doubles are kind of like the decimal point version of a long. They can hold even bigger values. If we need to go above that 5 quintillion number, which, hey, sometimes you're going to have to, then we start needing to rely on the object-oriented libraries that are built into some of these languages that allow us to have arbitrary size values. And we can do that because just as we started to learn that I'm pausing so we can get into the code stuff, once we fully understand how number systems work, nothing keeps us from writing a computer program that lets us hold any size value up into the number of bits for the amount of memory we have in our computer. We don't have to stop at 64 bits. We can go to 5 million bits, which lets us count really high, right? 2 to the 5 millionth power, big. Okay. Now we start getting into numbers that I'm going to have trouble reading. Right? Well, pretty much everybody will have trouble reading, but you get my point. All these share the same pattern. These aren't just arbitrary values we picked out of the sky. They're all powers of 2. Plus or minus 2 to the 7th power, plus or minus 2 to the 15th power, because one of these bits is used for sign, plus or minus 2 to the 31st power, plus or minus 2 to the 63rd power. 0 to either 2 to the 8th or 2 to the 16th, because we use the entire size for the value. Floats are kind of like almost 2 values put together. It's an int before the decimal point, and it's a char after the decimal point, since we don't need to hold positive and negative numbers. A double is 64 bits signed before decimal point and 32 bits unsigned after decimal point. So for a total of 96 bits. So this was 48 bits total. This is 96 bits total. So to store a double is going to take an amount of memory inside your computer that is 96 bits to store a single double. Even if it's a super tiny number, if you're just storing 3.14, if you're storing that as a double, it's going to have a whole lot of zeros in it, but it's going to use 96 bits to represent 3.14. That makes sense? All right. So it's kind of, does this kind of spell out what's happening under the hood with these things? All right. And again, this all goes back to that whole Y2K problem. And really, this goes back to the Y2K problem showed us the reason why we had this stuff before that. This stuff existed because memory used to be really, really, really expensive, and we needed different size Tupperware for holding different size values so that we didn't waste all of our computer memory to hold the number 6. Okay. The one last thing we throw in here, though, is something called a Boolean. All of our languages have something called a Boolean. This is effectively a true or false value. 1 or 0. Most of our older languages under the hood store this as a 1 or a 0, a numeric value, just like chars. Computers like numbers, so it's stored as a numeric value. In fact, really, all of our even modern programming languages under the hood are storing this as a numeric value. In older languages like Java or like C and C++, not that it makes any sense, but you could do math with trues and falses. You could say true plus false is 1. That doesn't have an equivalent in real life. Like you would never add true plus false and think that you would get it. It's like saying, okay, what's an ice cream cone, plus I don't know, a TV remote, and having that come out with some sort of answer like that makes sense. All right, that's not something we would try to represent in computer programming, because it's not something we would try to represent in real life. Usually, if it doesn't make sense in real life, it's not going to make sense in computer programming either. But because of the way it's actually stored under the hood, if you were using an older programming language before they kind of hid those details, you technically could do math with Booleans. All right. Modernly, with like Java and C#, it's still being represented as 0s and 1s, but it kind of packages it up in such a way that if you try to say true plus 7, it wouldn't fly. It would say this is not a numeric type. You can't do math stuff with this. It's used for other things. It's used for asking questions. If it's true that it's sunny outside, make sure you grab your sunglasses. That kind of stuff. Asking questions. Keep counting down to 0, and once you hit 0, the shuttle launches. That's doing repetition. Okay. All right, questions about this these are called our primitive types. All right, so if you were to summarize this, modern languages have the ability to hold whole sign numbers, has the ability to represent characters, has the ability to represent decimal point values, and it has the ability to represent trues and falses. So really, this whole slide says we know how to store 4 different kinds of values. Make sense? All right. So a statement I'm going to say, and this goes back to, first of all, I'm starting with this premise that all of our modern programming languages came from the C programming language. That isn't to say that C is the very, very, very first programming language that ever existed, but realistically, it's the first programming language that really mattered for what we think of as modern software development. Okay, the C programming language was a language built for writing operating systems. And we talked about operating systems as that layer that sits between the human being and the computer. So we don't have to walk up and turn on little light bulbs, vacuum tubes, and stuff like that, right? So in terms of how human beings today think of computers, we always think about them in terms of having some piece of software that's sitting between us and the computer. So we needed a programming language in order to write that piece of software, okay? And C was that language. All right. So I like to make this statement that all programs, no matter what the program you're writing is, it begins and ends with something called main, because that's how C started their program. Okay. In C, we had a function called main, and when you ran your program, the very first thing the operating system did is it went and looked for main, and it said, what does line 1 inside of main say I should do? Then what does line 2 say? Then what does line 3 say? And does it send me off to some other function? No problem. I'm just going to follow the yellow brick road. Okay, but I'm going to start with main. That's true in C. That's true in C++. That's true in Java, C#, Objective-C, Swift. Insert your favorite language. If you've done Python stuff, it hides it from you, but I promise you, when you run a Python program, there is something called _main_. Starts with main. Okay? Why is it still this way? It's not broken. Why fix it? Now, then you say, well, why do we have all these new languages? Why didn't we just stick with C? Well, C was originally designed to write operating systems, but it was designed with the power of computers that existed back then. When computers first came out, humans didn't really consider all the problems we'd be able to solve with computers. As computers got more powerful with more memory and more affordable and all these things, human beings came up with more and more things that we can do with those programming languages, we'll do with those computers, which then required us to have programming languages that were more and more capable. All right. So one of the weaknesses of a language like C, and we really actually talked about this already. Remember the procedural versus object-oriented telephone? Pile of wires versus the thing looks like a telephone. C is the pile of wires. C++ looks like the telephone. C++ introduced something called objects. C++ is an object-oriented programming language. Effectively, it's the C programming language with a couple of quality life improvements, but with the addition of something called an object. All right. Which we talked about then as being basically a piece of Tupperware that you can shove all the details into that you don't need to use, and then you poke a couple of holes for the parts of it you actually need to interface with. All right. But C++ did not change a majority of the stuff that was under the hood because it already worked. It just identified the couple of things that, maybe were too cryptic or maybe made human beings a little error prone, that kind of stuff. And maybe it put some protections around those, although it didn't put protections around the Booleans. So in C++, you could still do math with Booleans. So it didn't fix everything, but it made a couple of little fixes like that. But largely C++ is the C programming language that supports object-oriented programming. Okay. What about Java? Well, Java is effectively the C++ language, which has everything that's in C++. But what it did is it dumped the concept of something called a struct, which we'll talk about, because it basically said, oh, objects are objects, and you can represent a struct as just a normal object that doesn't have functions attached to it. Don't worry about what that means. When we get to object-oriented programming, I'll explain. All right. So it did that. It kind of improved upon the object-oriented nature of the language. But also, one of the things that Java did is it reduced the number of things the programmer had to type, where they always typed the same thing every single time they wrote code. So there's a bunch of stuff in older languages, and even modern languages, but a bunch of stuff in older languages that if you look at 100 programs, 100% of them would have the same 3 lines of code identical in some place. Java would have said, okay, if you're always going to write those 3 lines of code, we'll go ahead and write them for you behind the scenes so you don't have to type them out. They're still there. It's still running. The Java compilers are written in C++. All right. So, but we're just not going to make the programmer write extra crap that they write the same way every single time. Make sense? C# is effectively Java. We could probably sort of stop there with the example of C#. There was the lawsuit and all this stuff, but they made a couple of improvements from Java. But again, it's a very similar type stuff. If C++ is a full step upgrade to C, Java would be a full step upgrade to from C++. C# would be maybe a quarter of a step upgrade from Java. They did add a couple of things in there, but mostly they just cleared getting sued is what they did with it. But now C# is a super popular language. There's probably, if you look at current jobs out there, if you were applying as a software engineer today, you would probably likely get a job as either a Java developer, a C# developer, or a C++ developer. Potentially a C developer if you're working on like embedded machines, some like writing software for like washing machines and dishwashers and stuff like that. Those small kind of, those computers that they're very specific, general specific purpose type things. They typically run on kind of a small subset of the C programming language. But largely you're going to, if you're doing native computer programming, writing video games, writing business applications, that kind of stuff, you're Java, C#, C++. All right. Python would be more on the data science, artificial intelligence side of things, scientific research type of stuff. So also super common, Python developer. But they wouldn't write Microsoft Word using Python. Just doesn't lend itself to that problem. All right, so let's look at some comparisons. So this is Hello World, the simple Hello World program written in a bunch of different languages. Now remember what I said before, all programs begin and end with main. So this is old school C. We have main, printf hello world. C++, we have main, cout hello world. C#, we have main, console.writeline hello world. Java, we have main, system.out.println hello world. Objective-C, we have main, nslog hello world. What are we seeing in there? Remember NS? Next step, Apple computers today is Apple logo on Next computers, which is all over the place if you look under the hood. All right, so now I understand if you look at this in a little bit deeper detail, like, okay, well, there are some differences, but as a starting point, they all look like C. They're all recognizable from C, right? They have some extra things thrown in there and maybe have a little bit, it is kind of funny how they keep changing how they print stuff. Like, why couldn't they just left the function just be called print to display something to the screen? Like, printf printed to the screen. Why did they have to do cout for C++? Technically, you can still include the standard input output from C and still use that in C++, but they switched it to this IO stream thing, which the nature of how output to the screen changed in more modern languages, but that doesn't mean they have to change our function. They can just say, let us still say printf, and you just make it work the different way it needs to work behind the scenes. But they didn't do that because back then it still needed to seem super geeky so you can make more money, right? All right, and we keep doing that because that's called job security. We make our languages seem really cryptic, and then even as you get into programming, you'll start not documenting your code very well like you should. That way you're the only one that can maintain it, so they can't fire you. Yeah, so you're learning all the tricks today. All right, don't do that, but you can do that. Okay. You're not big enough yet. Only the big companies get sued. What are they gonna sue any of us for? Like Starburst, Crocs. Yeah. You can sue Microsoft for, $700 million and they'll settle with you for $3 million and you're happy. There's a lot of Big Macs for $3 million. All right. So without going into the details here of each individual one, we could all kind of appreciate that we have 5 different programming languages that all look very, very, very similar. We all kind of believe that, okay, Littman says that they all came from C. Here's this language from the 1950s. Here's a language from the late 60s. Here's a much newer language. This is in the 90s. Well, actually, this is, very early 2000s, late 90s. This is kind of early-ish 90s. Objective-C has actually been around kind of at the same time as C++. It's the object-oriented version of C. So Objective-C says object-oriented C. C++, I mentioned, is the object-oriented version of C. So why do we need both those languages? I'll give you a hint. C++ was adopted by Microsoft. Back then, did Apple ever adopt the same thing that Microsoft did? One of the main backers of Objective-C was Apple. So we have two different languages that effectively are kind of doing the same thing that only really exist because two companies couldn't agree with each other. You know, you go back that far, Apple computers didn't have USB for a long, long time. They had something called FireWire. You know, Apple's famous for having different shaped plugs, right? And every 5 minutes when they come out with a new device, they change the plug on you, right? It's Apple's, that's their MO. We see it in the programming languages too. All right. So here's now we're at the point we're diving into the code. So as a reminder, how do human beings solve problems? We remember stuff, we ask questions, we have repetition. I mentioned that 100% of programming languages have facilities for these three things. All right. We had a mapping. Memory in programming languages is usually done through something called a variable. Asking questions in a programming language is usually done through something called a conditional or an if statement. Repetition in a programming language is done through something called loops or functions and procedures. We're going to see each of these as an initial example today. So I'm going to kind of throw it all out there, and then we'll work backwards and fill in the details. All right. So there's already a link to this up on Blackboard. And if you want to use a different tool than this, if you've programmed before and you have a favorite editor or something like that, you can. But realistically, I really encourage everybody to use this tool because I'm going to expect you to submit a link to your program whenever you submit programming assignments. And the tool I'm going to introduce you to lets you conveniently submit a link. It also means I don't have to try to help you debug 50 different software applications that you put on your computer. So we're going to use a tool called Online GDB. So that's onlinegdb.com. It's going to bring you to a thing that looks like this. This is actually a pretty cool tool. So we have something called an IDE. This is an integrated development environment. Now that sounds like smart, right? Sounds kind of cryptic. Effectively, this is fancy text editor for computer programmers. That's what an IDE is. They do a lot of color coding stuff. Some of them will auto indent code for you. A lot of times they'll have a little play button built in there, so they'll go ahead and compile and run the program for you, so you don't have to do that. Quality of life things that computer programmers need that aren't really part of your computer programming skill set, but certainly make your life easier. All right. I historically would always encourage people to write code completely by hand at first, do all the indenting and stuff like that at first, and you'll see me do things like that when I write stuff. But modernly, pretty much everybody starts inside of an IDE. So the one thing I'd warn you against is make sure that you're looking for areas where the IDE is making you look better than what you typed, and so you appreciate what it's doing for you. Okay. So in this case, we're using an online IDE called Online GDB. And what's really cool about this is you can select from all these different programming languages. So right inside of a web browser, you can write in all these different languages. All right, so I'm going to switch this to C++, since that's the language we're going to be using in here. And notice that immediately it goes ahead and writes your hello world program. Gives you your starting point. In fact, that's something that I will typically tell you to, whenever you start a computer program, write hello world first, compile and run the program. That way, you have a good development environment. It's ready to go. Any bugs that happen from that point forward were things that you introduced, not because there's something wrong with the C++ compiler or something like that. All right, that makes some sense. All right. Now I'm going to go ahead and log in here. There's another site that you could, there's another site that I'm going to be introducing at some point, but right now we use online GDB instead of this. But there's something called GitHub. How many of you have heard of GitHub before? All right. GitHub, a lot of people have heard of it, but not that many people have used it. So when you've seen GitHub, a lot of times it's because you were downloading some piece of software and it gave you a GitHub link to where it's stored. GitHub is what's called a source code management tool. Really, the tool is a program called Git, G-I-T, which runs on Unix and Linux. Well, initially ran on Unix and Linux. GitHub is a web-based place to store your Git repositories. All right, and really, it's kind of, let's call it the industry standard for storing your source code. And the model they use is first of all, they give the professional version of GitHub away free for students. So if you want to go and sign up for a GitHub account, make sure you do their education thing so you don't have the limitations of their normal free account. The normal free account only lets you have public, I think, at least historically. Now they might let you have public and private repositories, but they limit you in some way. But you have a limited account if you don't want to pay for anything. As a student, you have a full-fledged account and you still don't have to pay for anything. All right. And what this lets you do is it lets you create kind of storage containers, folders up in the cloud to hold your code for your project. But beyond that, it's not just like Dropbox or Microsoft or Google's cloud storage stuff. It is specifically for source code type stuff. So what you can do is, as you continue to work on your project and you make updates to it, you commit and you push those changes to the cloud, and it keeps track of all the different iterations of your project. And let's say you're working on a big piece of software and you release version 1.0 of it. You can say 1.0 is now locked. And then what you do is you might say, I'm going to start working on 2.0 of this, but we're not changing 1.0. That's considered the current version of it. There may be some bug fixes or whatever, but we're going to start a new major release. So what you would do is you would create a second branch of that same project where you now are making updates to this, which do not impact the original one. If you've ever clicked on a GitHub link, sometimes you might go to, it might take you to a place that, if it's already got executables on there, it might say, okay, well, if you're a Mac user, use this one. If you're a Windows user, use this one. Maybe there's another one that says, for the latest beta, click here. For the latest stable version, click here, that kind of stuff. So it's storing multiple iterations of code. But GitHub is very much a place for computer programmers to store their stuff. From an education perspective, it allows you to give me a link to your code. So I don't, especially as your projects get bigger, initially, all your projects are going to be single documents. But before long, as we get into object-oriented programming, your project might have 2 or 3 different source code files. Then you get even bigger. Maybe you'll have 10 or 20 source code files. My preference would be that you don't turn something into Blackboard with 20 attachments. Instead, you give me a single link that I could click on that link and it takes me to, in this case, either online GDB or GitHub. GitHub's a little bit cryptic to use, which is why I don't start with it. Plus, online GDB already has this kind of built into it. But you can just provide me a link, which allows me to go in and look at your code, run your code, all that stuff, but I can't change your code. All right, so you're safe with those links. Another thing, just for your information when you're working on your assignments and stuff over time, when you do share your project using online GDB, what it's doing is it's sharing a current snapshot of your project at that point in time. So if you do make changes to it after that point in time, and I go back and click one of your old links, I'll see your old version of your code. All right. So it's actually kind of a convenient way of you maybe starting, because a lot of the times I have the assignments build on top of each other. Right. So, you might have assignment 1, which does one thing. Assignment 2 is to further expand that to do 2 things, something like that. So if I haven't gotten to the grading yet, you don't have to worry that you're overwriting that project, because your old link will show me your homework 1 and your new link will show me your homework 2, the changes you've made since then. It's a convenient thing where GitHub does not actually do that without you purposely making it do that, where you would create a separate branch for each homework assignment or a whole separate repository for each homework assignment, which becomes not so friendly when you consider that you might have 3 or 4 assignments in a row that all are basically the same assignment that just keeps one-upping itself. So you probably wouldn't want to start over with a brand new repository every single time. You want to just keep updating your current repository with the new code. Well, I would be able to go into your GitHub link and see your changes you've made by clicking around and doing some stuff. But your GitHub link is always going to take me to the current state of your code, where Online GDB takes me to a snapshot of your code when you submitted it, which is also better. All right. So I don't remember what I logged into this with, but let's see. Did I log in with? Yep. All right. I just want to make sure I'm in the right thing here. So here, I'm just going to create a new project. We have C++ as the name of the file, or C++ is the language. Notice it already named my file main.cpp. It will do this stuff for you, and you don't get to change the name of that source file, because it's kind of how Online GDB works. It knows the file it's going to run is called main.cpp, where in real life, if you were writing a C++ program, you could name your file that has main in it. You can name the file lol.cpp if you wanted to. Doesn't matter, but this is just a caveat that Online GDB uses. Doesn't matter, it creates the file for you. All right, so I've chosen C++. It's already written some code for me. I'll walk through the code and explain it here in a minute. But you can make sure it's working by just clicking run, and you're going to see hello world showing up down here at the bottom. All right, so your homework for Tuesday will be to get hello world working in Online GDB and submit a screenshot of it. Effectively, after Tuesday, I know every single one of you has a working software development environment. That makes sense? So, homework. Create a hello world program using Online GDB and submit. Actually, you know what? You don't even need to submit a screenshot. I'll just show you right here. Let's say I'm done with my homework. You just click share, copy that link. That is a snapshot into your code. Submit. Well, do this. Share the code and submit the link. Here is an example of a working hello world program. I'll give you my code. Don't just turn my code back into me. Write it yourself on your own. I mean, you can copy it, because the purpose of this assignment is not to learn to program. It's to show me that you have now a working thing that you can do your homework with. Make sense? All right. All right. So that's your initial introduction into Online GDB. So now what I'm going to do is, in our last 9 minutes here, I'm going to effectively just do kind of this core dump of showing you examples of remembering things, asking questions, repetition. These are all things that we will deep dive into as we make a second pass, but I'm going to show you their existence so you know how all these things ultimately exist in the C++ language. All right. So we have something called variables. So this is us mimicking memory. The syntax is type, variable name equals value with a semicolon. And I'll remind you, I think I've said it before, but in all of these modern languages, they are case sensitive. Spelling matters, case sensitivity matters. So, as an example, I can say int age is equal to 21. This is the type, int. This is the variable name, age equals an initial value. All right. Similarly, though, I don't actually have to give it an initial value if I don't want to. I would say you probably usually would give it an initial value, but nothing actually keeps me from doing int num2, defining a variable without a value, and then I can say num2 is equal to 7. So this first part of it, this brings a variable into existence. This tells your operating system, I need a memory location to hold an integer, which we now know can hold plus or minus 2.1 billion, those numbers. I want to call it age because I'm a human being and I like words. So whenever I want the value of that variable, I'm going to ask for the age. And you're going to go and look it up using your magic tricks, and you're going to bring me back the value associated with age. All right. But similarly, I can say age is equal to 14 if I want. They're variables, so the value can vary. Okay. So you can do it all in one fell swoop if you know what value you want it to start with, or you can bring the variable into existence, effectively asking the operating system to create a space for it. And then you can give it a value at a later point in time, and you can change the value again. You can say num2 is equal to 13. And the value will always be whatever the last value of the variable was. So if I come down here and I say cout age, well, let me just do it like this so I don't have to show you the next thing. I do cout age started off as 21. I changed it to 14 right here. So it's going to print out a 14. There's my 14. Same thing if I say show me num2. Num2 started off as nothing. I then gave it the value 7. I then gave it a new value 13. It's going to print out a 13. Make sense? If I never give it a value, num2, and then I print it out, it's going to give me a 0. What we're seeing there is the default value that C++ gave an integer is a 0. Never, never, never use that. Never rely on any programming language. Never rely on default values because you never know when those might change. If you want a variable to have a value, you put it there and then use it. So never use a variable before it's been given a value. We talked earlier that these newer languages have fixed some things from older languages. If we were in Java here, it would yell at us and say, this variable may not have been initialized. We would get an error. Okay? So good programming practice. Variables are meant to help you remember things. Don't try to remember nothing. Before you use a variable, put a value in it. Whether you put a value in it when you first bring it into existence, like we did here, or you bring it into existence and then put a value into it at some later point in time. Make sense? All right. So there's quick examples of some variables, and variables can be all of the types we've talked about and then more that we haven't talked about. So we can have variables of type byte, short, int, long, float, double, Boolean, char. The one thing I'm going to throw out there just because I forgot to mention it, and it's kind of a weird trivia thing. We go back here to our primitive types. I mentioned that whenever you're going to hold a whole sign number, you'll usually use int. Logic might suggest that if you're going to hold a floating point number, you'd usually use float. It's actually not the default. The default is typically double. So it's kind of interesting. They say that ints are good enough. We're not going to use longs because we're only going to use 32-bit numbers. But for floating point numbers, double tends to be the default, which actually takes it a bigger footprint than a float. But that's modern day programming, call it best practices. Realistically, it's not really a best practice because at home you would put your leftovers into the right size Tupperware container, but modern day programmers, we don't do that. We use ints if we're holding whole numbers unless they're not big enough, and we use doubles if we're holding floating point numbers unless they're not big enough. All right. So now let's just add a couple of things in here. Now we're going to ask a question. So we're going to say if, throw it in. So that's variables. Ask questions. Syntax is if, lowercase I, open parenthesis, some Boolean expression, closing parenthesis, opening curly brace, 0 or more statements, closing curly brace. Optionally, you can have an else. 0 or more statements, closing curly brace. So giving you a quick example of that. If age is greater than or equal to 21. See out. Have a drink. It could be milk or something. These are so judgy. Else, take a hike. All right, so I'm asking a question. I'm asking a question about the value of this variable. If whatever age currently holds is at least 21, we're going to print out this. Otherwise, we're going to print out something else. So right now it is 21. We'll run this. And we get a, I changed it. I changed it to 14. Remember? So let me get rid of a couple of these extraneous things with our examples. Age is 21. We'll go ahead and run this. So now it's going to say have a drink. If I change this to 14 and I don't change any of the rest of the stuff, now it's going to say take a hike. Okay. If I change it to 88, it's greater than or equal to 21. It's going to be have a drink. Maybe we just say see your doctor. All right. So now we've seen variables. We've seen asking questions. We'll come back on Tuesday and we're going to look at loops quickly. I'll also show you functions quickly. These are all things that I typically hit in a certain order and I talk about the background, but what I'm going to do is I'm throwing them all at you initially, and then we'll go back in and fill in the gaps. So you're effectively seeing, frankly, the entire programming language in small fell swoops. The link, you click share up here. Just click the share button and it'll bring up this link. You can share. So yeah, just give me this link right here. Okay. All right, I'll see everybody on Tuesday.